Hello, my kiddos and kiddas. This is Ms. Lloyd, and we are looking at using fundamental identities. So for our trig identities, a lot of these are ones that my students have already seen. The cofunction identities, I don't personally use a ton. Quotient and reciprocal identities, though, those can be used all the time. Pythagorean identities are some of my favorites because of the first one. It's a really great pickup line. And then our even odd identities. So just an idea of what you're looking at. And these are all identities that I let my students use on formula sheets, so it's not something I have them memorize, although I'm pretty sure most of them have the sine squared plus cosine squared equal to 1 memorized just because I've scarred them for life with a pickup line for it. So this first question, first example, we're going to be using the conditions. They tell us our tangent is equal to 1/3 and that our cosine is negative. And they want to design all the values of all the 6 trig functions. I did have a typo there earlier. So here they are telling us that I'm looking in an area, or what I like to look at first, I look at the signs. So we're saying our tangent is positive, but our cosine is negative. So I'm trying to figure out a place where that's going to happen. And the only place where that happens, or tan is positive and cosine is negative at the same time, is going to be in the third quadrant. And then I also like to keep in mind that whenever I'm doing tangent of any kind of angle, that is equal to the opposite over the adjacent. So then my opposite is going to be 1 and my adjacent is going to be 3. And so we could also see it as y over x value. And because cosine, or the x value, is supposed to be negative, then I know that the y also has to be negative in order to make our tangent positive. So another reason why we're in this area. So that means that I'm going 3 for my x value and 1 for my y value. And I have my little triangle. So now in order to find my sine and my cosine, they want all 6 trig functions. That means that I need to have my hypotenuse. So I've got to figure out what this hypotenuse is, which I can use the Pythagorean theorem for. So now I've got my hypotenuse being the square root of 10, and I have everything that I need in order to find all 6 of my trig functions. Remember our sine, we are using SOHCAHTOA in this case. My sine is going to be the opposite over the hypotenuse. And I need to rationalize that denominator. My cosine is going to be adjacent over hypotenuse. Still need to rationalize. And they already gave me my tangent. And so now I'm going to find those reciprocals. So the reciprocal of sine is cosecant, or CSC. So I'm just flipping my fraction. I'm going to flip the original fraction because then that way I won't have to rationalize again. The reciprocal of cosine is my secant, or SEC. And again, I'm just flipping that fraction from the beginning, so I don't have to rationalize again. And then the reciprocal of my tangent is my cotangent, so that would just be 3 over 1 or 3. And we're done. We've got all 6. This next bit, we're going to be factoring some expressions. So for this particular situation, I have a cosine that's squared. So this is very reminiscent of our difference of squares. So I could take the square root here, the square root here, and know that in order for the middle term to have canceled out, that means that I should have opposite signs in the middle. So plus and minus. And then that's as far as we can go. We no longer have a cosine that is squared or any trig function that is squared. And we don't want to FOIL it back again because then we would be right back where we were originally. I have some other for my students, but I'm going to say that for them. Here we're trying to simplify this down as much as possible. Most of the time the goal is to try to get only one trig function. So here, one of my first tricks, I guess, whenever it comes to doing this kind of simplifying, is anything that's not already sine or cosine, I try to turn it into sine or cosine. So here my cosecant I know is technically 1 over sine, and cotangent is cosine over sine. And so I can do a little bit of simplifying here. We can now see that I have the same denominator for both of these, so I can combine this into one fraction, all over sine of x. And then this 1 minus cosine squared x at the top is reminiscent of our Pythagorean identity of sine squared plus cosine squared equaling to 1. We would just have subtracted the cosine squared over, so that means all of that is actually equal to sine squared. And when I have a sine squared x over a sine x, this is very similar to if I had an x squared over an x. One of the x's would cancel out with what's on the bottom, and I would just be left with x itself. So the same thing happens here. One of the sines, technically it's sine times sine on top, would cancel out with one of the sines on the bottom, or the sine on the bottom, and I'm just left with sine of x. And then that's all that I have for you guys today. The rest I'm going to save for my students. If you found this helpful, please like and subscribe. If you think this could be helpful for someone else, please feel free to share. Spread the love.